So yes, this whole effort is difficult. And it, like I said, it did not lend itself to sound bites. Now, others, yes, had thought about the general problem. One of the most brilliant astrophysicists of the turn of the century, Sir Arthur Eddington, from a seminal book that he wrote titled The Internal Constitution of the Stars, he suspected, I quote from that book, "I think that the suspicion has been generally entertained that the stars are the crucibles in which the lighter atoms, which abound in the nebulae, are compounded into more complex elements." People knew the universe had larger elements. They knew. You ask, well, where did it come from? Was the universe born that way? Well, this is way before the Big Bang. So they had either somehow the universe happened that way, or they're made. And he suspected that they were made. In 1920, atomic physics was going strong. There was the beginnings of nuclear physics, but it was the dawn of quantum mechanics. The full understanding of particles and atoms and nuclei was still to come. But he suspected that they were on the right track. You could ask the question, where else in the entire cosmos would you make heavy elements but for the centers of stars? You want an exotic environment. You want an environment that if you have to slam light elements together to make heavy elements, where's that going to happen? It's not going to happen in your backyard. It's not going to happen in your kitchen. You need something as hot as you can imagine. And that's the centers of stars. That was well known at the time. But the real solution required the discovery of quantum mechanics in the 1920s. There's no way Eddington could have figured out the whole story. He was missing physics. Physics had to be invented to complete that story. Quantum mechanics, as I've alluded to many times, is the science of very small things, atoms and molecules. Something to consider, protons, if you want a hydrogen nucleus is a single proton. It's the lightest element, the simplest element. If you want to bring two hydrogen nuclei together, they're both positively charged, they're going to repel. They're going to repel. And so what do you do about it? Well, slam them together faster. They'll get a little closer before they repel. How do you make it go faster? One way to do it is to heat the soup. Heated gases, the particles move faster and faster and faster as the temperature rises. Get them close enough together so that they're within the domain of the strong nuclear force. When you get them close enough together, the strong force kicks in and binds the two protons together. They had to cross this, what we call potential barrier, though, this electromagnetic resistance of the two positive charges. This electrical resistance, they had to overcome that. As I said in one earlier lecture, it's like taking a toy truck and sort of rolling it up a hill, but you don't give it enough energy and it just sort of rolls back, and you sort of roll it a little faster. It gets higher up the hill and rolls back. But there's a speed with which you can roll it, and it hits all the way at the top and goes over. That's what's going on with these protons. Now, Eddington is not stupid. Eddington calculated the temperature of the center of a star. He got that right. You don't need quantum mechanics for that. He said it's 10 million degrees or so. Then he calculated the speed with which protons must approach each other in order to collide. You know what temperature he got? He got 1 billion degrees. That worried him because the two temperatures had no correspondence with. They are vastly different temperatures. If you want to rely on collisions in order to give you a heavier element, you might be telling yourself at this point, the stars are not the place. As hot as they are, it's not going to work. Tens of millions of degrees is far away from 1 billion degrees. So that's why there was as much resistance as there was at that time for considering stars to be the place where heavy elements would be formed. But there were the diehards that said, look, I don't care what you say. I don't know what you're saying. All I know is the hottest place I can think of is the center of the star in the whole galaxy. So if you want interesting atomic things to happen, nuclear things to happen, if we don't look there, I don't know where else to look. And that's the right attitude. Because it turns out that the speed of protons at 10 million degrees is enough to make them collide. But not by the traditional way you might think. There's a phenomenon in quantum mechanics that has no analog in everyday life, and it's called tunneling. Tunneling. Let's go back to my little truck. I'm trying to roll it up the hill. Here I'm trying to shove it up the hill, and it rolls back, and it's not enough energy. In quantum mechanics, depending on the ambient temperature and pressure and conditions, one of these times I roll the truck, a hole opens up through the mountain, and it goes through the mountain and comes out the other side. And it gets to the other side of that mountain for free. Now, that'd be pretty interesting if that happened in everyday life. But it doesn't. It happens in the realm of the atom. So that, in fact, these protons, which are trying to overcome their repulsion, some of them actually do connect at temperatures as low as tens of millions of degrees. You didn't need the billion degrees, but before quantum mechanics was discovered, there was no way to think about that problem. There was no way to answer that problem. There was no solution waiting for you. All right. Quantum mechanics tells us, all right, the temperature's hot enough to make your elements. That's good. Well, how about the relative amount of each element? That's another kind of question to ask of the SAR. Well, come the 1920s are over, quantum mechanics is in the can. 1931, there's an astrophysicist named Robert Atkinson. He published an extensive paper on what was going on inside of stars. And his abstract summarizes what he was after. Synthesis theory of stellar energy and of the origin of the elements, in which the various chemical elements are built up step by step from the lighter ones in stellar interiors by the successive incorporation of protons and electrons one at a time. So, we already accounted for the existence of elements, and he's trying to find a way where one by one you build up the elements. And in his paper, he talks about what kind of relative populations of the elements you would get. But he didn't have a chance of getting the right answer. He was missing a particle. He had the right physics, he's missing a particle. A year later, 1932, James Chadwick discovers the neutron. Now, you can't talk about nuclear physics without a neutron. Neutrons go hand in hand with protons in the nucleus. That's an incomplete theory. You left the salt out of the soup. No matter how smart you are, you weren't going to get the right answer without the neutron. Now, the fun part about neutrons is they don't have a charge. So here's a nucleus with this fat positive charge, and you take a neutron and toss it towards the nucleus, it just walks in the front door. There's nothing to resist it. So you can have a nucleus, feed it neutrons, and build up the count of particles inside the nucleus. You hand a neutron to the nucleus, no, it doesn't change the species. It's still hydrogen if you add a neutron to it. But we have a term for it. It's called an isotope. An isotope of an element is where you have a varying number of neutrons. You keep the number of protons for this. It turns out there are some elements where if you give them an extra neutron, they don't like the extra neutron. So spontaneously, again, we learned this from quantum mechanics, spontaneously, it's got the neutron in the nucleus and it said, neutron, give me a proton and an electron. The charges cancel between a proton and an electron as they are neutral in the neutron in the first place. So all the charges work out. So you give the atom a neutron, the neutron spontaneously becomes a proton and releases an electron. So almost for free, I got to have a proton join my nucleus. This process is a very effective way of building up elements. And it can happen swiftly. There's some, by the way, it may be that there's some elements, not maybe, it is true, that there's some elements where if you give them one neutron, they go unstable and they kick the whole neutron out again. But if they have two neutrons, they are stable. And given the time, they'll convert the neutrons to protons. So think about it. if you have a weak flux of neutrons into your atoms and into your nuclei, if you're an atom that's unstable with a neutron, you're not going to do anything with it. If you're stable with a neutron, fine, you'll mutate it into the next element up on the periodic table. But if you have a heavy stream of neutrons, maybe I just gave you one and you're unstable, but before you could release that neutron, another one comes in. Now you've got two. Turns out the nuclear physics of it say that I'm stable with two, even when I was not stable with one. So with two neutrons, I'm stable. Now I can undergo a decay again and turn my neutron into a proton and an electron. So it's simple. One is called slow neutron capture. The other is called fast neutron capture. The only lesson there is that now there are more ways to make elements. It's not just simply slamming protons together the macho way. There are also less spectacular ways of building up the population of elements on the periodic table. And when you combine all of those features, each one of them gives you a different mix of different elements, and put them all together, you begin to recover the exotic distribution of elements in the cosmos. You begin to recover why it is, for example, that on average, elements with an even number of protons are more abundant than the adjacent element that has an odd number of protons. That's odd. Those elements, they needed two particles to come in. You're actually slamming a helium nucleus in, you get two protons right off the bat. And you grow by just accumulating helium nuclei. So you're hopping in pairs. So if you look at the abundance on the chart, it's high here, down, high, down, all the way on up. Fascinating. And it all comes out of this analysis. Now, what about those collision cross-sections? Like I said, you don't get those. Those are hard. Those are hard. Turns out, just the facts of global politics, we got our collision cross-sections to feed the research that went into the 1957 paper by Burbage, Fowler, and Hoyle. Most of those collision cross-sections for the atomic nucleus came about from the research that went into the Manhattan Project, the American program to build the first atomic bomb in the Second World War. When you're at war, a lot of money gets spent. A lot of effort gets invested. Not because you're curious about the science, but because a weapon is being made. Your defense is paramount importance. And a sidelight of that fact, it's simple. A sidelight of that fact is we got from that research, once it became declassified, collisional cross-sections of particles moving in and out of an atomic nucleus. And it enabled those calculations in the first place. Now, of course, now that we know how to make the elements in the centers of stars, in particular in the centers of the high mass stars that have enough temperature and enough pressure to keep that going right on up the periodic table of elements, let's begin by asserting something that's not a strange concept, that stars are in the business of making energy. And to be in the business of making energy, that's all they know how to do. If you look at the sun, the cross-section of the sun, what you see is down in the center, that's the hottest place. It's much, much cooler out to the surface. And it's in the core, that's where all the thermonuclear fusion is going on. The sun is making heavier elements. It's converting hydrogen into helium. But that's not the interesting elements. The interesting ones are the ones that we're made of. So the ones we're made of, who's going to make those? Those are the high mass stars. They start out making hydrogen into helium, fusing the two, fusing hydrogen, becoming helium. There's a loss of mass there. You do the arithmetic. You start out with more mass than you ended up. What happened to the mass? It all got converted according to E equals mc squared, and you get an enormous amount of energy from that lost mass. All right, so now you go hydrogen and helium. High enough mass stars convert helium to carbon. They take 3 helium atoms and get carbon out of it. Then, if you have high enough mass, it'll keep cranking this through. It runs out of one element and starts manufacturing the next. It goes from helium to carbon, carbon to oxygen, oxygen to neon, and this continues. And it's getting energy at every phase, except it's not as efficient. It blows through those heavier elements very quickly, compared with how much time it spent converting hydrogen to helium. So, as it moves up the periodic table, one of the elements it's going to end up with is iron. Time to fuse iron. Well, let's go for it. All right, let's collapse a little bit, get the temperature up. We begin to fuse iron at extremely high temperatures, much higher than what the sun is doing right now, or at the centers of a star while it's converting hydrogen to helium. So we start fusing iron. There's a problem. If you fuse iron, it absorbs energy. It doesn't release energy. Now that's a bad day for the star, because a star only knows the creation of energy. It's that creation of energy that supports it from collapse. Without a source of energy, it is hosed. The star has nothing to hold itself up. So it gets to iron, it fuses iron. Not only is it not good for it, because it's not giving up any energy, it's actually absorbing energy. And the whole star destabilizes. And it collapses. It collapses in a matter of hours. And the collapse of that star rebounds from the center in a titanic explosion that is as luminous as 1 billion stars. And we call those objects supernovae. They're visible across the galaxy, across the universe. You're looking at an image of a galaxy halfway across the cosmos, and there's a little smudge there, but there's a bright light sticking on one of the spiral arms of the spiral galaxy. That's a supernova that just went off. These things happen in real time when they happen. You can watch them get brighter and watch them get dimmer as the explosion runs its course. Well, this is such an active place that, in fact, there's a lot of free neutrons running around and protons. And so not only did you manufacture elements on way to iron, there's a lot of manufacturing going on after iron as well. Slow neutron capture, fast neutron capture, a little bit extra fusion on the side. It is a trove of enriched chemical elements. One such remnant of a supernova is the Crab Nebula. The Crab Nebula is the remnant of a star that exploded and was seen. It was seen by the, well, actually, we think everyone on Earth saw it, but it was only recorded by the Chinese. AD 1054, July 4th. In the records of the Chinese records, there's a new star in the sky. We now know that was a supernova. We now know it was that supernova, making this residue, this explosive remains, this 2,000-year-old remains, which we have poetically referred to as the Crab Nebula. And you notice on it, there are these fibrous parts to it. Each one of those areas contains a strand of heavy elements lifted out of the center of the star and brought into the galaxy for the rest of the galaxy to share, so that subsequent stars that are made can make something other than the central star, like planets and even people. In the next one, it's another supernova remnant, Cassiopeia A, we happen to call it. It's in the constellation Cassiopeia. Cass A, you notice, once again, you'll see how sort of explosively thrust forth these gas clouds are. And if you analyze the chemical composition of each of those strands, you'll find very high iron and oxygen and carbon and all the things, all the elements that we've come to know and love as living beings that thrive on the heavy elements of the cosmos. So you combine all this. And what Burbage, Fowler, and Hoyle did was they took the well-tested tenets of quantum mechanics, combined it together with the physics of explosions and the latest collisional cross-sections for the atomic nuclei. And they also looked at all the nuclear pathways that can result based on those input parameters. Combine that also with basic stellar evolution theory And when you've done all of that, and you've done your homework, you account for not only the existence, but the distribution and the relative abundance of elements in the cosmos. And it was in 1957 where it was determined. Something about us that I will never forget, and I will tell as many people as I possibly can. And you might have expected it all along, but it remains true, not just figuratively, but literally, that we are all stardust. Welcome back to my favorite universe. Today, we're going to tackle a pretty hot topic, and that's the one that involves the search for planets in our galaxy. Now, the search for planets takes on many dimensions. You might think, well, why search at all? We're pretty sure the galaxy, the Milky Way galaxy, our galaxy, has planets in it because the sun has got 8 or 9 planets. Before the 1990s, our 8 or 9 planets were the only known planets in the galaxy. Right now, we happen to be rising through 100 planets known outside of the bounds of the solar system. And that number of planets were not discovered just because people were curious whether there were planets elsewhere in the galaxy. I always had the confidence that if we looked, we'd find them. No problem there. What's really going on here is that we're trying to find worlds that could support life. And if the sun is an ordinary star, not too bright, not too dim, not too hot, not too cold, not too massive, it's ordinary. And it's got all these planets, and one of them has life on it. Then imagine other ordinary stars in the galaxy. So it becomes an exercise of not just simply filling catalogs of planets, as we've done before searching for particular types of stars or even particular types of galaxies. We're looking for places that could have life. Now suppose for every ordinary star, no matter how many planets it had, one of those planets was capable of supporting life as we know it. So how many planets might that be in the whole galaxy? Well, how about the whole universe? Well, there are 100 billion stars in the galaxy. 100 billion. And in the whole universe, there's about 50 to 100 billion galaxies. You take those two numbers and multiply them. That gives you the total number of ordinary stars. That's a 1 followed by 21 zeros. 1 sextillion. Most people, nearly everyone, has never had an occasion to greet that number. 1 sextillion. But let me give you an idea of how big it is. It's 100,000 times bigger than the total number of all the sounds ever uttered by all human beings who have ever lived. That's how big that number is. That's how many stars there are in the universe, and perhaps that's how many planets there are capable of supporting life. Unless, of course, we're unusual. That's an unpleasant thought. I'd like to think that we're common. But let's take a look to get a sense of how many stars there are. In this view, we have a tiny piece of the sky pointed towards the center near the center of the Milky Way galaxy. It's towards the constellation Sagittarius. Sagittarius gets the award for having the most stars in it because those are the stars that trace out the constellation Sagittarius are sitting in front of our sight line that goes straight to the center of the galaxy. And all these stars are crammed in there. That's just stars in one patch of sky in our own galaxy. Imagine summing that up for the whole galaxy and across the universe. So, dare we think that we're alone? Now, it turns out, to theorize about there being other worlds, other places where you might find life, to theorize about that wasn't always met with support or praise. In fact, in the year 1600, there's Brother Giordano Bruno, who's a monk. He lost his life. How did he do that? Well, it wasn't really his fault. In the Square of Flowers in Rome, the Catholic Church burned him naked at the stake. Naked at the stake. And had he just been an ordinary heretic, they would have burned him without removing his clothes. But he was an impertinent and pertinacious heretic. Why? What was his crime? He suggested that the universe must be infinite because if it were not infinite, then it would have to be here instead of there. And how could it be in one place and not another? Because if it's finite, it's leaving out some space over here. So his philosophical sensibility told him that the universe must be infinite because it can't be one place and not another. Number one. Number two, from the vastness of this infinite universe, he concluded there must be many worlds beyond Earth just like Earth. And he was rather animate about this. This got him into deep trouble. Enough trouble for him to be burned at the stake. It was against Scripture, against Catholic interpretations of Scripture. In fact, there's a statue to him in the Square of Flowers in Rome. He's posed with his robe on. My last time in Rome, I had a pilgrimage to that statue, thinking to myself, they don't do that anymore, fortunately, because I'm talking about planets beyond Earth all the time. And not only is that work praised, but it sometimes makes headlines.
Thì X của chúng ta nó sẽ là ngay vị trí, đây nó ngay vị trí này, chúng ta chiếu vào trục OX, đúng không? Nó ngay biên dương, được chưa? Các bạn lưu ý điều đó cho thầy. Nói chung đồ thị nó rất là dễ các bạn. Nhiều bạn chúng ta cứ sợ về đồ thị, nhưng nhìn vào đồ thị là cho chúng ta biết được rất là nhiều điều. Và bài toán đồ thị là một trong những cái bài toán theo thầy đánh giá nó rất là hay, nó rất là thực tế, đúng không ạ? Nó dễ tưởng tượng, đúng không? Các bạn chú ý dạng này nha. Và bây giờ thầy trò chúng ta sẽ đi giải quyết các bài tập này xem coi nó như thế nào đây. Bài số 1. Đồ thị ly độ. Đồ thị ly độ của thời gian của một con lắc đơn dao động điều hòa được mô tả như cái hình này đây. Hãy mô tả dao động điều hòa của con lắc đơn. Thì cái này các bạn, câu A này các bạn chỉ cần ghi chữ ra thôi, đúng chưa? Các bạn chỉ cần ghi chữ ra cho thầy nha. Thì đối với cái câu A này các bạn chỉ cần ghi như sau, đúng không? Chúng ta thấy dao động của con lắc trên được đồ thị, có đồ thị là một đường hình sin, đúng không? Các bạn chú ý, chúng ta chỉ cần ghi là dao động điều hòa của con lắc trên, của con lắc đơn có đồ thị là một đường hình sin. Thế thôi, đó là câu A. Bây giờ câu B, thầy trò chúng ta sẽ đi giải quyết câu B. Đây là những trọng tâm của cái video này nha. Xác định biên độ, ly độ của con lắc đơn ở các thời điểm t bằng 0, t bằng 1, t bằng 2. Mình lưu ý điều này cho thầy. Trong dao động điều hòa thì ly độ, biên độ luôn luôn là một hằng số dương. Nó không bao giờ thay đổi được, đúng không ạ? Nhiều bạn cứ nói là biên độ biến đổi. Các bạn chờ thầy chút nha. Như vậy chỗ này các bạn coi xác